How's it going? There's water on my face. See? Water on my face. This is going to be on bomb calorimeters. So this is still in your thermochemistry notes. I believe it's question 3 in there. Very similar to a coffee cup calorimeter, just some small differences. So here's a picture of a bomb calorimeter. What they have here is you've got this nice insulated container, probably some water in here that they have a stirrer for. Your sample of whatever it is you're in here. So it could be a piece of food. Like if you're trying to figure out the number of calories in food, so it could be a piece of Twix candy bar. They're going to burn that and see how much heat that substance gives off. The more heat in it, the more calories. Okay, the more energy that item contains. So this thing would be completely closed off. They have ignition that lights it on fire. It burns. We see how much the temperature of the calorimeter increases. So they have a thermometer in here. Now, the nice thing is every bomb calorimeter has a certain heat capacity. So maybe it's like 10 kilojoules per degree Celsius. So they know that for every degree Celsius this calorimeter changes, how many kilojoules of heat are being given off. So it's set for each calorimeter. So that makes our problems just a little bit easier here as we do them. So the first one we're going to do here in our bomb calorimeter is going to be the reaction of vanadium with oxygen. So this is the combustion of vanadium forming vanadium oxide. Now if you notice here there is a 5 halves. You're probably not used to that. There's a 2.5 moles of oxygen. The reason you're going to see that quite a bit in these thermochemical equations is that they oftentimes want to keep this for every 1 mole of this compound. So to keep this as a 1 right here, they had to make this a fraction or a fractional coefficient. So more than likely this is an exothermic reaction since it is combustion of vanadium. So they're going to put 1 gram of vanadium. They're putting 1 gram of vanadium in the bomb calorimeter. The temperature of the calorimeter raises, about 1.5 degrees, 2 degrees, something like that, about a couple degrees. The heat capacity of this calorimeter, so remember I said every calorimeter has a certain heat capacity. The heat capacity is 8.78 kilojoules per degree Celsius. So that means that for every degree Celsius change inside that bomb calorimeter, that much heat had to be given off. Every degree Celsius the calorimeter goes up, that much heat had to be given off. So that's called the heat capacity of the calorimeter. Again, in this case, the Q of, and it tells us, wants to know how much heat is evolved in the reaction. So I know that our Q of reaction is negative, equals the Q of our calorimeter. Now, the Q of our calorimeter is going to be a little different. It will not be MC delta T. Notice our label here, just kilojoules per degree Celsius. So all you got to know for the calorimeter is how many degrees Celsius temperature change was there? Because we know for every 1 degree Celsius, how many kilojoules of heat were given off. So if we want to do the Q of the calorimeter, we just take 8.78 kilojoules per degree Celsius times our delta T, the 23.19 minus 21.43. So we're taking kilojoules per degree Celsius times degree Celsius, and you get about 15.5 kilojoules. So the Q of the calorimeter equals 15.5 kilojoules. Notice this is in kilojoules because that was in kilojoules. So that means the calorimeter gained that much heat as the vanadium was burning. That means our Q of the reaction is a negative 15.5 kilojoules. So our Q of reaction, in other words, the Q of this vanadium is a negative 15.5 kilojoules. Again, that is per 1 gram of vanadium because that's all they put in there. They didn't put a full mole of it in there. They only put 1 gram. Okay, so next question would say, what would you expect Q of reaction to be if 2 grams were burned? Well, if that was a negative 15.5 for 1 gram, if we had 2 grams, that would be double. Okay, or if I asked you how many kilojoules per mole, I know that this is per 1 gram of vanadium, so multiply by the molar mass of vanadium to see how many kilojoules would be per mole. okay, which would be a pretty common question. So, to get it to 2 grams, I just double that, so it'd be about a negative 31 kilojoules of heat given off for that. One more question here. So this is the top of page 3 in your notes. Sorry, it's a little slanted. You guys can work that way, hopefully. Actually, straighten that out. So this one we want to know, what is the heat capacity of a bound calorimeter? Okay, we want to know what the heat capacity is. So what they usually do to figure that out is they put a substance in that they know how much energy it gives off. Okay, in this case, they're going to use methyl alcohol. So they know when 1 gram of methyl alcohol burns that it gives off exactly that much heat. They've studied it enough times. They know that 1 gram burning gives off that much heat. So we're trying to figure out what is the heat capacity of the calorimeter. So remember, that heat capacity of a calorimeter, the C of a calorimeter, is in kilojoules per degree Celsius. In other words, for every degree Celsius change, how many kilojoules of heat were given off. So that's all we got to do. We know that 19.93 kilojoules of heat, there were 19.93 kilojoules of heat, and the temperature changed this much, divided by 27.1 minus 23.72. That's just our change in temperature. I'm just trying to figure out how many kilojoules there was changed per 1 degree Celsius, because this number of kilojoules was per, what is that, about 3.5, 4 degrees Celsius. So when we do that, we get a specific heat of about 5.89 kilojoules per degree Celsius. So this specific heat capacity, or the heat capacity of this calorimeter, for every degree Celsius temperature change, the calorimeter raises by that many kilojoules. Okay, for every 5.89 kilojoules, it raises 1 degree Celsius. So if you had double this many kilojoules, the temperature would raise double that number of degrees. That's it.